Welcome to the Learning Hall. Today we are going to study a small chapter in mathematics, a theorem that is the foundation of mathematics, and more or less we all know that theorem. The theorem is called Pythagoras theorem. All of us have heard about it, even you have heard about it. Pythagoras theorem dates back to 500 to 600 BC, and the whole theorem is being named after Pythagoras because he was the first person who found out the proof of this theorem. After that, there have been a number of proofs done by others, and multiple names have come. Euclid has found the proof, Garfield, Bhaskara, and several other theorems have come. Today we are going to study a proof given which is the easier of all of them, and that is the proof given by the similarity of triangles. Let us see how we can prove the Pythagoras theorem through similarity of triangles. Here is the statement of the Pythagoras theorem. We know in a right angle triangle there is the perpendicular, a base, and a hypotenuse. The Pythagoras theorem states that perpendicular square plus base square is called hypotenuse, is equal to the hypotenuse square. We have explained it, and we have given a small diagram, a small right angle triangle at the bottom, ABC, and this triangle has a perpendicular P, a base B, and a hypotenuse H, and we have to prove that hypotenuse square is equal to perpendicular square plus base square. Let us see how we can prove this theorem. So, here is the triangle once again. We have redrawn the triangle ABC, right angled at B, and AB is the perpendicular, BC is the base, and AC is the hypotenuse. To prove the program, we will do a small construction. We will draw a line which is perpendicular to AC from B. That means BD is perpendicular to AC drawn from B. So, having done the construction, now the triangle is divided into two smaller triangles. In fact, we have three triangles now. Triangle ABD, which is right angled at B, triangle ABD, which is right angled at D, and triangle BCD, which is right angled at D as well. So these three are the triangles that we are going to consider. Now let us consider the big triangle ABC and the small triangle ABD. As you can see, both the triangles are right angled. Angle B and angle D are right angled. Angle A is common to both the triangles. Hence, the remaining angles are also equal, which means that triangle angle C is equal to angle ABD. By the same logic, these two triangles are similar. So we can write triangle ABC is similar to triangle ABD by angle-angle similarity criterion. By the same logic, now if we give our focus in triangle BDC and the big triangle ABC, we can see both the triangles are right angled. Angle ABC is right angled at B and angle BDC is right angled at D. Angle C is common, hence the remaining angle are also equal. So angle A is equal to angle DBC. So both the triangles are similar, and just like before, we can also write triangle ABC is similar to triangle BCD. Now Let us consider only the first triangle, first equation. In this first equation, we get by the system of similarity, we use this symbol of similarity, and we can say that AD by AB is equal to AB by AC. Let this be equation 1. How is this possible? Have we done the right thing? We can say that AD by AB are the sides of the smaller triangle, and the sides of the bigger triangle is corresponding to AD you will have AB, and corresponding to AB you will have AC. So this similarity holds for the first triangle. If we cross multiply, we will get AD into AC is equal to AB square. In fact, this is the first equation. Okay. Now this we are drawing from the first equation. Now let us draw a similar thing from the second equation, ABC and BCD. Here what do we get? We get here you will have AC, here you will get AC, BC, and you will get here, stop. So here we have DC. DC by BC is equal to BC by AC. By the same logic, we are going to use this equation. We have used this equation, and from here we are getting DC by BC by the same logic. DC by BC of the first, this triangle corresponds to BC by AC of the second triangle, of the bigger triangle. So if we cross multiply, we will get DC into AC is equal to BC square. This is the second equation. Let us have a look once again. Adding equations 1 and 2, we get AD into AC, AC into AD plus BC is equal to AB square plus BC square. Now if you look at this focus over here, AD plus DC will give you, AD plus DC will give you AC. So we get AC into AC is equal to AB squared plus BC squared, or AC squared is equal to AB squared plus BC squared. So this is the proof that we wanted to do. Also we can write this as AC is the hypotenuse, so hypotenuse square is equal to AB is perpendicular square plus base square. So here we have proved that the hypotenuse square is equal to the square of perpendicular and the square of the base. So you can see that we have proved the Pythagoras theorem through a simple method of similarity of triangles. Having done that, we will now do a similar exercise on the converse, which means that we will prove the converse of the Pythagoras theorem. Let us see how the converse of the Pythagoras theorem can be proved.